All right. We are going to get started with the labs. So the first thing that we're going to do actually before we dive into the content of the labs is, for those of you who want to, we're going to kind of walk you through getting set up with the compute environment. So the goal of the labs is, we've built sort of this code base that's meant to be an example of what a relatively production-ready deep learning code base looks like. So we don't really have time for everyone to kind of go through and sort of create that code base and run a bunch of experiments on it themselves this weekend, just because we're trying to pack a lot in. And so most of what we're going to do in the labs is just walk you through kind of the code base and how you would actually go about using it and what all the pieces do. And the idea is for you on your own time over the next month or so to go back through that code base and make sure you really understand all of it, run a bunch of experiments, try to improve it, and things like that. So there's no need to follow along on your laptop if you don't want to. But if you do want to, here is the way that you would do it. So there's some setup instructions in the text recognizer project repo, which is at this address at the top. Maybe Sergey, do you mind posting the address to the setup instructions in the Slack?
What are the setup? Oh, in the GitHub.
Mm-hmm.
I also just put it in there.
Okay, cool. And so once you can see this, the first thing that you're going to do is you're going to go to app.wandb.ai. So W&B is an experiment management framework that we're going to be using for this class. And they've also provided the compute environment that we're going to use. And so what you'll do is, once you see this app.wandb site, you'll click sign up. And I'm going to just sign up with an email address. So I'll create a new alias. And then I'll create a password. And then click sign up. And so you'll get taken to a page where it prompts you to enter your name and your username. So I'll make my user like Josh loves FSDL. And then it'll take you through some questions. So I train models every day. More layers equals better. Why do you train models?
You should make your font size a little bigger.
I think also we should have the light for the stage.
Yeah, are other people having trouble seeing the slides on the stage?
Yeah, the smaller fonts are hard to read.
Is it better now, or is it still a problem?
The light is needed for the video recording.
Okay, sure.
Okay. So now you should be dumped into your sort of WandB home. And the next thing that you're going to do is you're going to go to this URL. So it's your W&B profile. Or settings. And so then what you'll do to get access to the JupyterHub is you'll put in the token, which I believe is FSDL gradient Cajon. And I think this is in the Slack as well. Is then you click redeem. And it'll spend a few minutes getting started up. And so I'm just going to kind of leave this on the setup and not sort of wait for it to get fully set up. But if you're going through this process and you get to here and you wait for a few minutes and it's still not working, then post in the syshelp Slack channel. Oh, but it was faster than expected. So yeah, so when you get dumped in, you'll be in sort of a screen that looks like this. And so this is a Jupyter lab. And so this is basically like sort of a web-based way of running code and creating notebooks in an environment that's kind of already set up for you. And so each of you, when you sign up for this, will have access to two GPUs on your hub that you can use to train models. All right, anyone sort of having trouble with this? Okay, great. Yeah.
Just tell me what the hub access is again. Where is it?
It's in the Slack.
Slack.
All right, so I want to now dive into the first lab. And so the first thing I'm going to do is kind of introduce you to what the labs are all about and what we're going to cover over the course of these lab sessions. So to give you a quick outline, the first lab, so that's this one, is we're going to talk about the problem that we're trying to solve, how the code base is structured, and then we'll show you how to train a simple character predictor. And then what we're going to do is we're going to move on to a more complicated task, which is reading entire lines. And then this afternoon, we'll show you how we approach experiment management, so running experiments in parallel and storing the results so that you have access to them. And we'll give you a chance to try some things on your own later today that you can run overnight and see how well your models perform. Then later on, we'll have training the other parts of the pipeline, so the line detector model. And then we'll talk about how to do data management in this system and how to write tests and do continuous integration. And then finally, how we deploy this model as a web service so that you can actually use it as part of your app. But so the goals of this first lab are, we really want to understand the problem that we're trying to solve and at a high level how we're going to approach it. And then we'll train our first model. So what's the problem that we're trying to solve? So suppose that we're building an app, and that app is called Text Recognizer Pro, right? And like the goal of this app is you want to take a picture of a piece of paper that has some text on it, and then you want to press your user to press the submit button, and then they should get back just like a paragraph of text that corresponds to what they wrote on the page. Okay, so how are we actually going to approach this problem? There's kind of three modules of our system that are all going to interact with each other. So when the user presses submit, the raw data is going to be sent to a web backend. And that web backend interacts with a compiled prediction model. So this is actually your neural network that's being used to create the predictions. And that compiled prediction model is created through some model training part of your code base. And so in a little bit more detail, you'll receive a post request coming in that has an image with some byte string. And the web backend will decode that image into something that you can read, and then send that into our prediction model. And the prediction model has two parts. The first is a line detector. And the line detector, what that does is it looks at the entire raw image and it tries to extract individual lines of text. Each of those individual lines of text is passed to a line text recognizer. And the job of the line text recognizer is to turn the words in that line into text. And then finally, the line text recognizer is going to send the results from each of the lines back into the web backend, encode that into a prediction, and serve it up as an API. And so then the last thing to talk about is how does this compiled prediction model actually get created? Well, it's a combination of a data set and some training code, which will be trained into some model weights that will be then used to serve predictions. And so what we're going to talk about now is some of the aspects of how we set up the model training code. Then we'll talk in the next few labs about how we build this one of these models, which is the line text recognizer. Then lab 5, we'll talk about how we do line detection. Labs 6 and 7 will come back to the model training code and talk about things like how do we write good tests for machine learning model training. And then finally, in lab 8, we'll talk about the deployment aspect. All right, have there been any questions up until now about kind of the overall architecture of the labs and what we're trying to get out of them?
Well, there's one question in Slack, which is, will this scale up to reading other kinds of text, like maybe like a doctor's note?
I think, probably not, yeah. But what you can ask yourself is like, how could we make this more general? So how could we make it scale up to other types of text, right? But I think ultimately your model only does well on things that you've explicitly trained it on, right? And so we're only going to train it on things that look like a page that has some text on it. And so I wouldn't expect it to do well anywhere else.
No other question.
I have a quick question. So in this flow, are we going to discuss the paradigm where we develop the model in notebook and then productionize it in scripted way?
Yeah, so the question is, are we going to discuss the paradigm of where we develop the model in a notebook and then productionize it using a script? The answer is we're not going to discuss that workflow, and the reason why is that we don't really recommend that workflow. Like typically for deep learning, what we recommend doing is using notebooks to inspect your data, but then building your training pipeline using scripts and Python code, because it's just going to make everything that you do more reproducible, and it's going to allow you to go faster. All right, so now we'll move on to training a simple character prediction model, right? So what we're doing here is we're starting with, instead of starting with the entire problem, right? So starting with taking a picture of a page full of text and then outputting the transcription of that text into characters. Instead, what we'll start with is just the simplest possible version of that, which is predicting a single character based on handwriting. And so if you want to follow along, this is the place where you can go and kind of look at the code as we go through it. And maybe we should add this to Slack too, if that's possible, if you're on there. OK, so the first thing I want to talk about is just how is this code base structured. So if you look in the Lab 1 folder in the text recognizer project, then you'll see these 4 subfolders. And the notebooks folder, so this is basically, as we just discussed, this is for your Jupyter notebooks. And what we typically use these for is exploring data. So it's often really important in machine learning to get intimately familiar with your data and just really get a sense for what that data looks like and what its properties are. And so typically we'll do that with notebooks, and that's where they live. Then there's a folder called tasks. And what this contains is just convenient scripts for things that you're going to do a lot. So for running tests and for the training commands that you're going to run over and over again. Then there's the training folder. And so this contains the actual logic for running the training itself. And then finally, there's this text recognizer folder. And this is where the bulk of the code lives. And so let's look inside of that. Within text recognizer, you'll see a number of other subfolders. The first one is datasets. And so the distinction that I would make here is that this is not actually where your raw data lives. So most of the time what we recommend doing is having your sort of raw data live externally to your project code base. Because often you don't want your raw data to be sort of like incorporated in your version control system. But what this does contain is the logic for actually downloading that data if you have it saved in something like S3, and then doing all of your pre-processing and augmenting, and then loading it into TensorFlow so that you can train models on it. So that's the code that's contained in the datasets folder. The next folder I want to talk about is the networks folder. And so this is basically the logic for constructing your neural networks. And so what I mean by this is, like, this is where your dumb input-output mappings live, right? So if you have like a specific ConvNet architecture that says, like, I take an image and I output predictions, then sort of the logic for creating networks lives in this folder. You'll notice that there's also a models folder. The distinction between networks and models in this way of thinking about it is that models are like a wrapper that lives around a network and adds all of the functionality like loss functions and saving and loading and training and creating sort of human interpretable predictions that lives on top of your neural net and actually makes it useful. All right, and so the reason that we have this distinction is because this can save a lot of code duplication, because this way you can just, if you want to try a different neural network architecture, you can just create a different architecture within networks, and then hopefully most of your model code will be reusable. Then we have a folder for tests, and so this is where your regression tests live. And for example, one important type of test that we have will be checking to make sure that a model that you've trained performs well on specific important examples, right? So there were a lot of examples of, there were a lot of questions earlier about bias. And so for example, like one thing that you might do is you might write a bunch of tests that live in this test folder that check whether your model produces biased predictions on subsets of your data that are important for it to perform well on. And then finally, there's a weights folder. And this just contains the weights of whatever version of the model that we're using in production right now. There's a couple of other files here. One is character predictor. And this is really just like a wrapper for a model that allows it to recognize a single character, right? So typically, the models will be used in a batch setting, like when you're training them. And so this is just kind of a lightweight wrapper that allows you to serve up, to kind of take a single image in and serve up a single prediction, which is kind of actually the function that will be used in production. And then there's some utilities. OK, any questions about the code structure and how things are set up? And then next, we'll dive into some of the details about how we've implemented things here.
Networks folder is the child folder of peer of training, and training is outside networks, right? So
Mm-hmm.
training uses this networks folder to do the training?
Yeah, so the question is, what's the relationship between this networks folder and the training folder that we saw that lives outside of this? Yeah, so basically, the way that you can think about this is, everything in this folder, so in this text recognizer folder, should allow you to create sort of like a fully functional model that you could train if you wanted to. And so this has like all the way that you specify your neural network, the way that that neural network ingests and preprocesses data, the way it creates outputs, the optimizer that it would use, and all of the hyperparameters that it would use. But then you also need some sort of way of training models in a sort of like scalable and easy to use way. And that lives in the training folder, right? So that's like, how do you specify hyperparameters to training on the command line? How do you run hyperparameter sweeps and things like that? Any other questions? Great. Oh yeah, one more question. Mm-hmm.
For, say, for PyTorch, like data loader object, where would it fit in this structure?
For PyTorch data loader object, probably within the datasets folder. Yeah. OK. All right, so the next thing I want to do is introduce the data set that we're going to be using to start. So this is the URL if you want to follow along. And, but I think this is probably easier to just follow along as I go through it. So if you do find that URL, then it takes you to a IPython notebook. And this IPython notebook is visualizing the eMNIST data set. And so eMNIST is like, how many have trained a model on MNIST? OK, yeah, I would hope that it's everyone. It's almost everyone, but not quite. So that's maybe some of you didn't complete the requirements for the course. But so eMNIST data set is just like MNIST, but it has more classes, right? So instead of just 0 through 9, it also has other types of characters. And so if you create an eMNIST data set class, which is one of the classes in our datasets folder, and you print it, then it just gives you some statistics about it. So it's eMNIST data set, it has 80 classes, and these are the classes, right? So it's numbers, uppercase letters, lowercase letters, and a few basic symbols. So we've instantiated this eMNIST dataset class, and we have this thing called like lowercase eMNIST dataset. And then if we call this load or generate data function, what this is doing is it's actually going and if we don't have the data, the raw data saved locally, it'll actually go and download it, and then it'll like kind of load it into the dataset class. And so then you can print out the training dataset and the shape of the training dataset, the images and the labels. And so there's something like 700,000 images in this dataset, and they're 28 by 28, just like an MNIST. OK, so now we have a rough sense of like how much data that we have and how many classes. So the next thing I might want to do is look at visually, OK, what do these images look like? And so we can kind of loop through a few of the examples, and we can visualize them. And so this is kind of what the images in this data set look like. So again, it's very similar to MNIST images, but you also have other symbols other than just numbers. And so this is the data set that we're going to work with for the first part of the labs. Any questions about EMNIST? All right. The next thing I want to do is go a little bit more into detail about some of the code that we have in this repo. And so the first thing that we're going to look at is, remember we had this network folder that had these neural networks that I said were like dumb input-output mappings. And so let's actually look at one. Let's look at the MLP code base. And so what you'll notice if you open up this file is that we're defining a function called MLP that takes, what are the input and output shapes that we want it to have, how big are the layers, how many layers do we have, and then some dropout. And then it returns, so we have this like Python 3 forcing it to return a particular type. And in this case, it's returning a Keras model. Right? And so all this function is doing is, if you're familiar with the Keras syntax, it's creating a sequential model. And then it's it's like flattening the input that it gets, right? So if it's an image that's, say, 28 by 28, then it's, instead of giving it a 28 by 28 input, it's flattening that into a 28 times 28 vector. And then for each layer that we want to create, so for all of the layers that we're trying to create, then we're adding a dense layer of a specific size. So we're creating the network, and then finally we're doing a softmax on top of it. So a very simple, fully connected neural network. We could do something a little bit more complicated like a Linnet. Works very similarly. Again, similar function, similar syntax, but instead of adding dense layers, we're adding convolutional layers. Okay, but you'll notice that in those networks, we didn't actually define anything else like how it interacts with data or what the loss function is. And so that's what this model class does. And so this is in the models folder and this is the base model class. And so the thing to look at here is, the constructor for this class takes, what type of data set is it going to have as input, and then what network function are we going to use, right? So is that network function an MLP? Is it a Linnet, or is it something else? And then some arguments about data set and networks. And so then basically what we're doing here is we're just instantiating the data set class to create a data set that it can interact with. And then we're instantiating the network by calling the network function on the sort of the input and output shapes that the data set gives us. So the first thing that this model class is doing is it's sort of constructing the data set and the network for us. There's a couple of other things that this model code does. There's a couple of convenience functions to give you the shape of the images and the weights. And then there's a fit function. And so this fit function is like sort of the inner loop of our optimization algorithm, right? And so what we're doing here is we're compiling the network. So for those of you that are familiar with Keras, you'll recognize that this is essentially telling Keras what loss function and what optimizer we're going to use. And then it's converting our data set into a data set sequence, which is like the way that Keras likes to ingest data. And then we're calling the fit generator function of the network. And that's actually what's running the neural network optimization.
Excuse me, where do we have the network function, which is there?
Sorry, what was the question?
The network function, network underscore reference, where is it written?
The network function. So remember we have these networks, right? And so these networks are basically where we define the network functions. And so then when you're constructing a model, you'll say, you'll import a particular network function, and you'll pass that function as an argument to your model class. Okay, so we have this fit function that we can call. It's basically a lightweight wrapper around calling fit on the underlying Keras model itself. And then we have a few more things, right? So we have an evaluate function, and this allows us to sort of make predictions on an entire data set and then see how well the model does in that data set. And then we have loss functions, optimizers, metrics, and ways of loading and saving weights. And so the thing to notice here about the loss function, optimizer, and metrics are that for this model class, these things are just fixed, right? So we're always using categorical cross entropy. We're always using RMS prop. But the flexibility that this gives us is that we can subclass this base model class, and then we can do whatever we want with those things. So if we want the user to be able to pass those things in as predictions, then we can allow them to do something like that. Okay, so within models, on top of the base model, there's also a character model. And what this character model does is it essentially just subclasses the base model, but it also gives you this predict on image function. And so this predict on image function takes a single image as an input and then does sort of the pre-processing for that image that you need in order to make a prediction on it. So for example, if that image is stored as like raw unsigned integers, then our model expects its inputs to be floats between 0 and 1. And so we'll divide the values of that image by 255 so that they're in the right range. And then it sort of makes a prediction on those, and then like stores the prediction that it made and the confidence of that prediction, and returns them in sort of a way that is like going to be human readable. And so this is essentially just a function that allows you to make a single prediction on a single image. Okay, so the next thing I want to talk about is like taking a step back and going into the training code. And we have this run experiment.py. And so what this run experiment does is you have this function that takes an experiment config and then some other flags, right? And the experiment config is something that looks like this. And so it's like a dictionary that tells you, what data set you're going to use. So maybe the emness lines data set or whatever other data set that you've defined. And then it takes some arguments for that data set, whatever those might be, depends on the specifics of the data set. And then similarly, you specify a model and a network and some arguments for those things, and arguments for training. And so it's essentially loading this JSON file or this dictionary of all of the parameters that define your training run. So that's the config. And then what it does with that config is it uses it to sort of to import the specific data set that you're going to use, and then instantiate it, and load or generate the data, right? So download the data if it's not already saved locally. And then similarly for the model, it finds where that model class is that you specified, and loads it and creates a model with the arguments that you passed in. And then runs this function called train model that you pass the model and the data set objects into. And then once it's trained the model, it scores it, so it runs model.evaluate on the test set, and then gives you the test evaluation. Right, so basically what this function is doing is it's allowing you to specify your training run as a dictionary, so as a config, and that means that you can create as many of these configs as you want, and then it knows how to use that config to instantiate the training run. And so what is this train model function actually doing? Remember, this is the function that's being called at the end of this, this training file. And so this is just a very lightweight function that just calls model.fit, essentially. But allows you to add any sort of callbacks that you want into the Keras training procedure. OK, any questions? So that's kind of like a lightning tour of kind of what all the code is doing in the simplest possible version of this task, which is training a model to predict a single character. Are there any questions about sort of how we set this up or why or what the different parts of the code base are doing?
I saw we used the batch size of 128, and that's like we decided on the basis of how much GPU RAM is available, or there are other factors?
The question is, why did we choose batch size of 128? I don't know that that was a principled decision. Yeah,
Okay.
it's a hyperparameter, right? And so ultimately, you're going to want to select that based on how well your performance, how good your performance is on your validation set.
So you came up with this structure and design based upon your experience in running into problems. I'm curious what common problems you faced so that we can see, we can say, we're doing that too. We need to use your model in that place for this reason. Can you go over some things like that are problems that led to this design?
Yeah, that's a great question. So the question is, we have a specific structure for the code base that's sort of based on our experience of different problems that arise when you're building a machine learning code base. And the question is, can I talk about some problems that I've seen that cause us to choose this structure? So I think there's a lot, right? Like I think one really common thing that people do is they write everything as like one long script. And so you have like one long script that includes how you specify your neural network, how you make predictions on top of that, and and then how you actually do training. And so I think that's a great place to start if you're working on a new problem. You always want to add the minimum new lines of code so that you can catch bugs as quickly as possible. But as your code base gets more mature, it becomes really, really hard to collaborate on top of that. And you end up with a ton of code reuse because if everything is living in one file, but you're training 4 different types of neural nets, then you're defining the same things over and over again. And what's worse than that is that oftentimes when you make improvements in one part of the pipeline, like say that you change the way that you do dataset loading so that you can stream images into your model faster, then those changes won't always take effect in every single model because you have those pieces of code in different places. Let's see, what else can I talk about here? Yeah, I think one of the other principles here is just isolating the different possible sources of bugs. For example, one place that I see a lot of bugs is in data generation pipelines. So often, you'll try to be regularizing your images, and it'll turn out that you're over-regularizing, and so that makes the task actually impossible. And so if you have all that isolated inside of some dataset files, then you have toggles that allow you to switch datasets easily. Then you can just sort of very quickly test, okay, is the problem my dataset? Well, one thing I can do is I can try to take a dataset definition that I know works and use that with all the exact same settings I was using elsewhere. And so this type of structure allows you to do that because it's very modular. You can just swap this dataset for that dataset. Yeah, that's what comes to mind. It's a really good question.
I have a question. So, in real world, this kind of your data set with your data, it can take gigabytes, right?
Yeah.
So this data set and data preparation scripts can take a while to execute. So what is your strategy? Are you kind of run this experiment and you start from generating data, which can take up to several hours and models trained, or you kind of run the job asynchronously, you just generate this data set, put it somewhere like with JupyterHub or something like that, and it's done in another data pipeline, and this code only assumes that data already prepared for your experiment.
Yeah, so the question is, in the real world, you often have a lot of data. Loading it and editing it can be really slow. And so, how do you deal with that in this type of structure? I think, if you have parts of your data generation pipeline that are really slow, I would run them offline and then save the data somewhere. And then basically what this part of the code base should be doing is, it should be like telling you how to stream the data from your external code base in as efficient a way as possible. So like eventually you want to be, sort of taking data from disk and prefetching it to your GPU so that your GPU has it available when it's time to train the next batch and things like that. And then also doing any pre-processing that you can do on the fly. Sergey, do you want to add anything to that?
That's basically right. But yeah, we talk more about this in the data lecture. It's coming up.
Yeah. Yeah, I'll maybe do one more question. Yeah.
This certainly looks like the structure for training, but how about when you're in production inference?
Mm-hmm.
Would that differ some? Like how would you recommend you?
Yeah, so structure in production. We'll talk about that in later labs. Yeah, I'll do one more question, yeah.
So there's also a challenge with this kind of setup of Codebase. Sometimes like when you're jumping on a new project, so you jump on an existing project that's set up this way, and you want to like try some new experiments, there's always this tendency for you to go and like edit the code somewhere where the person already has a setup somewhere else, and you kind of don't see that setup or you're not used to that setup, and then you're kind of editing like in the wrong place, and you're like where you're doing some code reviews and you're messing up like the standard stuff. Is there a way to do that?
So is the question like how do you move toward this from an already mature code base, or is it like how do you build something like this from scratch without creating too much work for yourself?
The question is like how do you jump on this kind of setup without like okay, I'm saying like there's the other side, like the con of this kind of setup, it leads to like not too bad, but is that sometimes like someone wants to do an experiment somewhere else and the person starts to like do a new write a new stuff that has already written there before.
Right.
How do you prevent those kind of things happening?
Yeah. So how do you prevent people from sort of repeating work and from solving the same problems over and over again, and how do you collaborate effectively on a code base like this? Yeah, I think a lot of this comes down to just like following good sort of software development, like DevOps type practices, like using version control and and then like also just good team management practices. So like making sure that you're communicating about the types of things that you're working on. Yeah, I think also having a good way of looking at each other's experiments is also helpful. So if you have like a visualization set up where you can go and see what your teammates have tried and like what the loss curves look like, then that can prevent you from trying the same things as well. Great, I'm going to move on. All right, so the next thing I want to do is let's actually go and train some models. So I'm going to go back to the Jupyter lab that we set up, and I'm going to open up a terminal. There we go. And then I'm going to paste in this, this training script. And so we're running, we're using pipenv, which I'll talk about in a second, to run experiment.py. And we're passing in these arguments. So we want to use emnist dataset and character model and with an MLP network and then batch size of 256. Oh, I think I need to be in the right folder. So, yeah, so we need to make sure our environment is installed. So what we're doing here is like we've specified the requirements that you need in order to run these experiments, and we're just making sure that we have those loaded in our environment.
You actually want sync dash D for the dev requirements.
Sync dash D. Should I rerun that?
Yeah.
Yeah, so just as a quick aside, so thinking about dependency management, the tool that we're using for dependency management here is pipenv. And there's a couple of other dependency management tools for Python. We're using this one because we want to be able to specify our dependencies flexibly. So we want to be able to just run, when we realize we need a package, just install that package, in a really lightweight way without needing to figure out like the specific version of the package that we want. But then we also want to be able to pin the exact versions of things that we need really easily so that we can make sure in our production environment we have the exact right versions of all the packages that we have installed, and we don't run into any issues with different versions of Python packages causing us to have bugs or make wrong predictions in production. And so pipenv is a tool for doing that. There's a few different sort of things that you can set up within a pipenv. One is a pip file, and the pip file is just a way of at a high level specifying what dependencies you have, right? So we're saying like for IPDB, for example, we're okay with having any version of that. Like we're not going to specify which version of that we have. But then the pip file.lock, what that allows you to do, what that does is it saves, for this environment that you're running things in, here are the exact versions of everything that we have. And so then you can use that to install the exact same version of everything. And then the other nice, cool thing that you can do with pipenv is you can look at the dependency graph. So you can look at kind of what are all our dependencies and what do those things depend on. And so it's a nice way of just managing the dependencies in your environment. Pipenv is good. I also like pyenv. I use that sometimes as well. But yeah, we're still installing dependencies here.
Guess maybe a good time for a question.
Yeah.
Someone asks pipenv versus virtual and versus conda. Someone else asks, why are we not using conda? Maybe I should answer it.
Yeah, you should answer.
Yeah, so I think conda is good because it installs CUDA and optimized numeric libraries along with the Python libraries that rely on them. Conda is also not good because its package versions tend to trail behind the latest package versions, and it's kind of a separate ecosystem of packages in some sense. So I prefer just the standard, PI packages, and then we can optimize ourselves the hardware that we're running on, just installing CUDA ourselves, and then installing TensorFlow from the normal source.
Yeah.
So I don't like conda for that reason. And also, we will be deploying to this deployment target called AWS Lambda, which doesn't really support conda. So if you have, conda is a pretty heavyweight thing. So if you're deploying somewhere that maybe you don't have that capacity to install it, then you can't really use it.
Yeah, I would just add to that, conda is really trying to be a sort of one-stop shop for scientific computing packages. And so that means that it solves a lot of problems, or it tries to solve a lot of problems, like dependency management, package, being a package store, installing, making sure that all of your libraries use the best sort of numerical tools that they can to run as fast as possible. And so as a result of that, it's huge. It's multiple gigabytes. And I just prefer lightweight tools where they just do exactly what you need them to do, rather than doing a bunch of other stuff that could create problems when you put things into production.
Yeah. So virtual and create. So there's three things I think you want. The first is the ability to specify dependencies exactly, very easily. So in pipenv, you say, I want any version of NumPy, but exactly version 1.14 of TensorFlow. And so then when I say pipenv lock, it'll figure out TensorFlow expects NumPy of these versions, but maybe my other library, pandas, expects NumPy versions of these other versions. So what's a version of NumPy that satisfies both of these things that I care about? And it locks everything to a mutually satisfactory version. VirtualAmp doesn't do that, right? You would still have to hope that you get the right versions. The second thing you want is to be able to create a virtual environment. So you don't want the packages you use in a given repository to be installed on the system in a system-wide way. You want them to kind of live with that project. So pipenv does that. It actually uses virtual env behind the scenes. So it installs everything into a virtual env. You just don't really see it. And then the third thing you want is separating production dependencies from development dependencies. The reason for that is because, like, we need Jupyter to develop because we want to use the notebook, but we definitely don't need Jupyter when we deploy, and it's very heavyweight, so it's nice to not have it. And so pip file, we can say production dependencies, development dependencies. So virtual env doesn't do that either. The tool that I would point people to is called Poetry. So Poetry is kind of like pipenv.
Cool. Yeah, so it looks like now that we've installed our environment, the model training is starting, and our loss appears to be going down. So that's good. And yeah, I would encourage you to play around with this on your own. You know, see if you can make it work in your environment, and see if you can make improvements to the model. And that's a good thing to do, you know, tonight or you're on your own time after the class.